Now I want to talk a little bit more about mechanical energy. And we generally break this into two categories, potential energy and kinetic energy. So potential energy is stored energy. Energy that's not necessarily moving something right now, but it could in the future. This is going to come either from the position of the object or some other unique properties of the object. So for example, a stretched spring, its position allows it to move at some point in the future. A ball above the ground could be moving if you dropped it. Or something like gasoline or a piece of wood have potential energy because they could be burnt to release the energy in those chemical bonds. We're going to focus in this chapter on something called gravitational potential energy, which is, again, from the position of an object. This depends on three variables: mass, gravity, and height. And so we put those together into an equation. Potential energy is equal to mass times gravity times height. All you need to do to calculate the potential energy of an object is measure its mass. You know gravity is 9.8 meters per second squared as long as you're on Earth, and measure the height off the ground. So a more massive object higher off the ground has greater potential energy. Kinetic energy, on the other hand, is the energy of motion. This comes from moving masses which can exert forces. We call it kinetic energy. It's the energy of motion. This little diagram shows you a conversion between potential energy and kinetic energy. The equation for kinetic energy is 1/2 mv squared, or 1/2 mass times velocity squared. Kinetic energy increases both with the mass of an object and with the speed of an object. But you'll notice that the v, speed, is squared, so speed makes a bigger difference here in kinetic energy. Let's take a look at a couple examples of word problems here. A 2-kilogram rock is at the edge of a cliff 20 meters above a lake. It becomes loose and falls toward the water below. Calculate its potential and kinetic energy when it's at the top and when it's halfway down. Its speed is 14 meters per second at the halfway point. So what information do we have and what do we need? We want to find its starting kinetic energy, its starting potential energy, and then its potential and kinetic halfway down. We know the mass of the rock, we know the height of the cliff, and we know its speed at the halfway part. We also know the equations for potential, kinetic, and we can assume that the rock is at rest when it starts. So, at the top of the cliff, the mass is 2 kilograms, gravity is 9.8, and it's 20 meters above the ground. So the potential energy, mass times gravity times height, is 392 joules. The kinetic energy at the very top is 0 joules, right? 1/2 mv squared. When v is 0, it doesn't have any kinetic energy, so that's easy to solve. At the halfway point, the mass is still 2 kilograms, gravity is still 9.8. The only difference is now it's halfway down, so its height is half of what it used to be, 10 meters off the ground. The kinetic energy halfway down, again, 1/2 m. Now we're doing v squared. Now it actually does have a velocity, so we can put a number in here. 14 meters per second squared times 2 times a half gives us 196 joules halfway down. And, not a coincidence here, it's now half potential and half kinetic. We'll talk about that more as we talk about energy transforming.